Welcome to my YouTube channel, Dhanesh here. This is the fifth video on gradient descent. See, we have covered all the concepts, how this algorithm works, everything we covered in the last four videos. So in this video, we are going to implement a Python program we are going to implement a Python program to show how this gradient descent works. So here the implementation of Python we are going to discuss. See the equation. See, you can see the dou j by dou m. Dou stands for the partial derivative and j is the cost function. The last video we discussed these aspects. J is the cost function or loss function or error function or objective function. All these things denotes the same thing only. So it is the partial dou j by dou m is the partial derivative with respect to m, dou j by dou m. So this equation we derived in the last video. It is equal to 2 by n into error into x. This is dou j by dou m, where m is the weight of the network. Normally it is the slope. We call it as in neural networks and machine learning, we call it as m as the weight. And dou j by dou b, j is the cost function and b is the bias, and we are differentiating, we are taking a partial derivative with respect to b. Why we are going for partial derivative? We already discussed, because the cost function depends on two variables. One is the weight and the bias, m and b. That's why we are going for partial derivative, and dou j by dou b is equal to 2 by n into error. Error means the predicted value minus actual value. See, here we have the sigma summation as well. In the program we include this. See, now we are going to discuss about a machine learning model to implement this. See, what is a machine learning model? See, we have a model. For example, this is the equation for the machine learning model. Y is equal to 8x squared plus 9. Here 8 is the weight of this. 8 stands for the weight and 9 stands for the bias. So we can tell 8 is m and 9 is b, right? So we will come up, see, we will have a data. See, we have x and y. So the program should come up with this equation. And that equation can be used for prediction. This is the way a machine learning model works. See, normally in a program we will give input and output. We will get the output. We will give input and we will get the output. In a machine learning model, see, we will provide both the inputs and the output, and we will come up with a machine learning model by using the input and the output. So our output should be this equation. This equation, in the sense, we need to come up with this 8 and 9. 8 stands for the weight and 9 stands for the bias. So we will provide equations. For example, when you substitute x is equal to 0, y is equal to 9. So we can get values like x and y values. You can get it. You are getting my point. So x and y values should be like this. You can substitute here. For example, this is the value of x and this is the value of y, the corresponding. When x is 0, y is 9. This is one value. When x is 1, you will get, we are substituting x as 1. Then y should be 8 plus 9. That is, you can get it as 17. So different inputs you will 17. When x should be, we will provide x as 2. You will get y as 25. So like this, y will be 25. Like this, you will give data to this program, and finally you need to come up with this model. Y is equal to 8x square plus 9. that model will be used for future prediction. This is the concept of our machine learning models. So now we will see all these aspects, whatever I am discussing, all these aspects we discussed in the previous videos. So we just for your understanding, we have come up all these aspects once again. So now I will do a program. So we are importing NumPy. See, NumPy, NumPy stands for numerical Python, which contains powerful n-dimensional array objects. When we discuss about huge arrays, so NumPy is the best option. So we have we imported NumPy, and we are defining a function gradient underscore descent. It takes two parameters. One is the input variable, and that is the x, and the output variable, that is y. So we have two, and we have weight and bias. See, I already discussed. Weight stands for m is the weight and bias is b, and those two we initialized to 0. Now we need to see, in the previous videos we discussed that we have numerical gradient descent. It's a repetitive process. We need to do that process. How it works, I clearly explained in the previous video. You please watch it. There also we discussed about the iterations. It's a iterative process. It's a repetitive process. So here we are taking the iterations. We are taking. Let us assume that it is 1000. So we are running this program in a Python shell only. You can run it in PyCharm or Jupyter Notebook, anywhere you can run it. So the iterations I have taken as 1000. Now I need another variable n, so that should be the length of the input or output variable, how many rows of data we are having. So that here right, this how many rows of data you are having. So n, I am taking it as length. Then this input variable we will copy it and give it there. So that will give the number, the length of the the number of rows of the data. So that is the variable n. See, in the previous videos we clearly discussed about learning rate. So that is an important parameter in the in this machine learning concepts. Learning rate we clearly discussed in the previous videos. In machine learning and in statistics, learning rate is a concept we are using it in machine learning and statistics. The learning rate is a tuning parameter we use in any optimization algorithm. It's a tuning parameter. We are using it in gradient descent as well as a tuning parameter that can be used in any optimization algorithm, and even gradient descent is an optimization algorithm. So that determines the step size. So this learning rate, I am talking about learning rate, that determines the step size. The step size of each iteration when we move forward towards the minimum of the cost function. See, our aim is to minimize the error, minimize the cost function. Cost function denotes error only. To minimize this cost function, how many baby steps that we need to take? So the size of the baby step determines the step size. The size of the baby step is determined by a parameter known as learning rate. So learning rate, it is denoted by the letter alpha. So here we are taking the learning rate. See, that is another parameter, learning underscore rate. So we can take it as some value. You can give it and you can change it based on your assumptions. You can change it. So let me take it as 0.2. The learning rate and the number of iterations, I have given it as 1000 here. So this 1000 we can change it to 10,000 or 100. So by varying the iterations and the learning rate, we can optimize this model. So that's what we do it here. So we are taking the learning rate as let us assume that I told its value is between 0 and 1. Let us assume that it is 0.2. If the learning rate is very small, the model, the training of that model progresses very slowly. So if it is very high, it will give some undesirable outputs for the cost function. So that's what it usually happens. So this is all about learning rate alpha. So here we have taken learning rate as let us assume it as 0.2. Then we have we will include a loop for loop we will put. So this is we will put it as we have the range of, so we will iterate through this. We have iterations, right? So we need to go through all this. So we have this, so that we have done it. Now this is what happening, we are iterating through this. So then we can understand, we need to get the values. See, we have the predicted value. See, our equation, our model is, this is what, right? See, the y is equal to mx plus c, that's the equation. So there y stands for y underscore, it is, let it be the predicted value, that is predicted is equal to m means the weight, network weight, we have already initialized there, weight into x means the input variable. So I am taking it as the input variable here. So it is here, we have the input variable, that is we have to keep it here. So it is input variable y underscore predicted is equal to, this is the model, weight into input variable plus you have the bias. So this is the equation, this is the model, this is our so we need to optimize the weight and the bias. So we are iterating through this loop. And one more important aspect here, it is the cost function. For this model, the cost function we need to minimize. So what would be the I am taking it as cost underscore or function, that variable. So that variable we already discussed in the previous videos. So its equation is 1 slash n. N is the length of the input variable, that means the number of rows, 1 by n into, here the summation sigma is there. So here we have sum of this is the when we differentiated partial derivative, when we have taken, we have the exponent, it is 2 square of it is, we need to put it there. Then 4 here we will take this value as in the value means, so this value, that means the error, see, it would be the predicted minus the output variable. So error will be the predicted means this error is always the predicted value minus the actual value means the output variable, that is the actual value for the y. So this is the cost function, it is 1 by n. Now we need to close the bracket, right? It would be, I am closing the bracket. so it would be like this. So I closed the bracket. Okay, now it is perfect. So y underscore predicted, we got it, and the cost function, we got it. It is 1 by n. This sum stands for the sigma. So you know the formula. It is, you know, the power exponent 2. That previous videos we clearly, you know, depicted the, you know, mathematical equation of cost function that is written programmatically in Python program. We have, you know, this y underscore predicted minus output variable gives the error. So that's, we are iterating through that. So that's what we have done. Now see, now we need the partial derivatives. One is for the weight and another one is for the, you know, bias. So it is like this. You can write it as same. You have the this one, the weight, that is it is, you know, this one, dou j by dou m and dou j by dou p. This is what we are going to write programmatically, how it would be. So dou j by dou m, that is the derivative of the weight. So we are writing it as weight underscore derivative. Derivative means when you differentiate, what's the output you are getting, that's the derivative. So weight underscore derivative is equal to, you can write it as, see this formula, well, it is 2 by n. So you can write it as 2 by n into, see here I didn't put the sigma. So this we have the summation sigma. Say sum here we have. So I am writing it as here I can write it as 2 by n, 2 slash n. Here I denote it's a small n. 2 by n into then we will, here we will get the sum, that function, then sum into what is here, it is input variable, that is x. See here you have to multiply with x. See here you have an x, so this x stands for our input variable. So this input variable into input variable into the error means the, you know, you can use the predicted minus the that is y predicted minus the output variable. So input variable into you can write it as again you will get it as, so the same thing you can copy it here. It is simple, so you can copy it like this, y predicted minus output variable. So that's what we need to do it here. So this is done. This is the weight underscore derivative. Now you need the bias underscore derivative. So I am going to write bias underscore derivative. That one should be the same thing, but you won't get the input variable in this formula. This formula we derived, this x is not there, x is the input variable. So the same thing without, you know, input variable. So that will give you the, you know, see in the previous equation you need to understand, you need one more bracket here. Am I right? Input variables here, one more bracket is needed, because, you know, that is it's a double bracket is needed here, so that's needed. So now bias underscore derivative, the same thing without x. So I can copy it and you know, I will remove the input variable from there. So it will work like this. So this one should be this one, but I am, you know, going to remove the input variable, because in this formula for the bias, the partial derivative, x is not here, here x is there. So x means the input variable here. I am going to remove that. So input variable, I am removing it from here for the see, even this bracket is not needed for here actually. That's also I have removed. So this is the bias of derivative. Now see the important formula I already discussed. The key formula here we will see we will use here is I have written here in the previous videos. See x, this is the another formula. I plus 1 is equal to x I minus alpha into f dash xi. Please watch the previous videos, so everything it is clearly mentioned. So this is the formula we use for gradient descent. See x I plus 1 is equal to, we derived this equation in the previous videos, xi minus alpha is the learning rate, alpha into f dash xi. So this xi plus 1, this x can be changed with m and b. For m and b we need to use this equation. For m and b we need to use this equation. For both m and b we needed this equation. So this equation we already derived in the previous videos. So we are going to write that equation. So here m is the weight. So weight is equal to weight minus weight is equal to weight minus learning rate, alpha. Here we have written as alpha. This alpha is the learning rate. So we can copy that variable. So it is you can get it like this. This is your learning rate that I put it here. So weight is equal to weight minus learning rate into this weight derivative, that whatever we got it here in the above step. So that's we have written weight is equal to weight minus learning rate into, see this is alpha into f dash derivative is the dou j by f dash, and dy by dx and f dash x both denotes the same thing. See f dash, this dash signifies first derivative. If double dash means it is second derivative. So this dou j by dou m is f dash xi only, the derivative. So that's why we put weight underscore derivative. Now in the same way you can write bias. Say bias is equal to, you can write it as, so we have to define bias. Bias minus, bias is equal to bias minus again learning rate, that is learning rate is this, control C, control V, then bias underscore derivative, that is control C into your formula is this, then you have the bias underscore derivative. So this is what this is the logic we need to implement. Now we will print all these variables. You have the weight, we need to understand weight here, then we have the bias, let me see how these variables will come, bias, then you have the I, it is the variable I. Now we have this cost function. Cost function is, this is the variable. So all these things, our aim is to minimize the cost function. These are all the variables we need. So now we need to give the input variables and output variables here. So I am going to give the input variable. So input variable should be, I am going to give it, inside here. So input variable, it is, we have this thing. I am giving it as a, number array. So input variable, it is equal to, we can give it as np dot array. So the values, some values we will give. It is we can give it as 0. See, I have already this column. So this is here. See, you have this 0, 1, 2, like that. So I am giving 0, 1, 2, 3, 4, and that's the number array for input variable. Now I have the output variable. That's also we will calculate. Finally, we will come up with a machine learning model for M and B with minimum cost function. That's what we usually do. Then np dot array. Then this is you can write it as you can get it as the values as 9, 17, 25. We have already these values, 33 or 41. See, 9, 17, 25, 33, 41. So this array also. Now we need to call that function, right? So gradient descent. So this function we are going to call now. So in this function, it is we need to copy it here and we will call it here. So that's what we have done all the aspects. Now let me see. Let me run this program. So what we will do is see. We will see. Let me see any error is there. So I will run this. So when I am running this, so let me see how it is looking. See, it is. See, it's showing no error, but you can see the values. It's printing. See, around we have given 1000 iterations. It's running now. So we can see the cost function, the values. First it is giving the value of m. M is the network weight, then the bias, then the value of I, then cost function. So that's what this program is doing. See the cost function. If you see the last data, see it is giving INF, infinity. In Python, INF stands for infinity. For this variable, the cost function is actually increasing. Even this m and b, see our value of m and b, I have already told you it is 8 and 9. It's nowhere it's matching, right? It's not 8 and 9. See, it is it's not matching with our values. See, it is giving a different result. See, and the cost function, it is increasing. See, it is beginning, it was less, then finally it increased, and cost function is increasing means again we need to change the learning rate. We need to minimize the learning rate. So we will see. We put it as 0.2. Now let me put it as 0.1. Let me see how it is happening. So if it is let me put it as 0.2. Let me put it as 0.18. So let us see how it's going. 0.18. Let me see the output. So I am running the module now. So let me see the output. So from 0.2 I came up to 0.18. So the cost function for 0.18, we can see it as, let me see it, it is the cost function here. Again, one thing I could see is the cost function here. If you analyze it, it is it's in the positive side. See, it is plus 295, then 295, then it is exponent. You can see it is 302 here. So again, the cost function, it is increasing only. We need to get a minimum value. So from 0.2 we again reduced it to 0.18, but it's not working. So now it is again, the cost function is increasing, and the weighted bias is nowhere near to our, see, we know the model, so it's nowhere near to this our weighted bias. So the cost function is also increasing. See, it is from plus 2 exponent 297, then it is increasing to 302. So this 0. The value we have given 18 also not working. Let me give 0.16 and see it. See the output, we will check it. So the output, it will be again the cost function. We will see, our aim is to minimize the cost function, should decrease. We have to, our model should be in such a way that the cost function should decrease. That's what we need to do. So let me see how the cost function is decreasing or increasing here. I believe it's again increasing. It's in the positive side, and the M and B, the weight and the bias, is not near to our values. So again we need to go back. So again here I could see plus 117, here plus 118, here exponent plus 119. The cost function is increasing, and this weight and bias is nowhere near to our value. See, our value, it is 8 and 9. See, here you have the model 8 and 9 at the weight and bias. So it's nowhere near. So let me change to 0.16 to 15. Let me run the program. So I am running it. It is it is 0.15. Now let me see it, how the cost function is working. Is it decreasing or increasing? We need to see it. So here the cost function, we need to understand it. So the cost function, it will be, let's wait and see how the cost function, is it increasing or decreasing. So here we could see again, we have it is again it is 791. Here it is 8081. So it is the cost function for this again increasing. So we will try with the 0.12. Let me see how it works for this value. Yeah, now it's changing. See, even our weight and bias is somewhat closer to our values. So you can see here the cost function, now it is decreasing. It's and our values also somewhat closer to our weight and bias. You can see here, it's really interesting. See, this thing when the cost function it is reduced, see now you can see even the weight it is almost 8.0000 and the bias it is 8.999, it is closer to 9, and this cost function, see here you can see it as minus 29. See this minus 29 is smaller than, you can see here, the previous exponent, it is e raised to minus 29, that is smaller than the previous values. If you see the previous values means it is minus 10, see minus 14, minus 19, so minus 19 is bigger than minus 29, so our final value is minus 29, it is decreasing, so it is negative exponent e raised to minus 29, so it started with minus 8, minus 9, so minus 13, see minus 20, and finally the cost function is decreasing at this value. So when we have given 0.12, the cost function is decreasing, and let me try with 0.13 as well. So let me see whether the cost function is decreasing or increasing, and we got exactly somewhat similar to our weighted bias as well. So this is the optimization, we are somewhat closer. So in that range only we need to optimize this model. See again we are closer, and it is in between, I believe it is in between 0.12 and 0.13. Am I right? Here also it is decreasing. See 29 it becomes minus 30. So 0.12, and I will try 0.11, then if it is changing means it would be between 0.12 and 13. Here also it's decreasing only, it's in between 0.1 and 0.11 and 0.13. So this is the way we need to optimize this. See, but the weight and bias also you can see it is 8.000 and 8.999. So here also it's decreasing only in this value as well. So here also the cost function is decreasing. So this is really interesting. See here it is minus 29, it is decreasing for this value as well. Now 0.1, let me try what will happen at 0.1. It's decreasing. In this value as well, it's the cost function, it is decreasing, so it's somewhere near to 0.1 and 0.11, like that. It is again it's decreasing the cost function, and the weight and the bias also it's somewhat closer. It's really interesting, this trial and error approach. You see, now we can try this. This is 0.1, right? Let me try this value, 0.09. So this is lesser than 0.1. So how it works? Let me try it. Is it working or it's? It's again decreasing. It's the cost function, and it's the weight and bias, it's giving the proper values, and the cost function is decreasing. Yeah, it's again we need to go back. That's what. So like this, by trial and error, you can find out the minimum of a cost function. So this is the approach we usually do. I think you have understood this. See, now I will try with 0.05. Well, let me see what it will happen, and this is the last trial, I believe. So it would be so here it is it's again it's decreasing. The cost function is decreasing, and the weight and bias also almost same. So it's between 0.0 like this. By adjusting the weight and bias, you can by adjusting it again, it's decreasing. So if it is 0. Let me try with this value, the last one, 0.01. Let me see what it will happen. So, and we can optimize for that. See, there it's again varying. See, it's 8 point, yeah. Cost function also, it is I believe. See here, you can see again the cost function. It is decreasing only. It is the weight and bias, but it's not proper. It is somewhat it's not closer to that. The cost function, it is fine. It is decreasing. So we can, like this, we can optimize the value of learning rate somewhere, and this is the approach we need. By trial and error, we can come up with the minimum value of the cost function. So this is the we need to do this. So this is all about a gradient descent. Yeah, thanks for watching.